Hey everyone, Mr. Armitage here. Now in this video, we are going to be doing the first of the hypothesis tests that we didn't do in class. So a National Cancer Institute study published in 1991 examined the incidence of cancer in dogs. Of 827 dogs whose owners used the weed killer 2,4-D on their lawns or gardens, 473 were found to have cancer. Only 19 of the 130 dogs that had not been exposed to this herbicide had cancer. So what are we doing here? What are we comparing? Because unlike the previous ones, words like proportion, percent, average aren't anywhere in this problem. So we have to think about what is happening to it. Okay? We are treating these dogs as either having cancer or not having cancer. Okay? Two outcomes. Cancer, no cancer. I guess we're going to call a success as one of the dogs having cancer, which is how stats works. Okay. So one thing we need to look at then is we have success, failure in this case. Okay, cancer, no cancer. And so each of these two things here, 827, okay, and 473 of those had cancer versus, I'm just going to use green or not, versus 19 out of 130. So we don't have like some overarching proportion or percent of dogs who get cancer. All we have is, well, two different percents. Okay, we could describe both of these numbers as percent of dogs who got cancer, right? And so let's set up two groups. Okay, so before we get into the hypotheses, let's go ahead and look at the groups. So here we have, let's see, N sub C will be, oh no, not C, we don't want C, we want weed killer or herbicide. So N sub H and N sub O for organic, whatever. So that means we'd have X sub H, X sub O, and then we'd have P hat sub H and P hat sub O. All right, so what are we trying to see here? Are we trying to see that the herbicide increases cancer risk? Okay, so our null hypothesis would be that it doesn't, right? That nothing changes, that nothing happened. So that would mean that P sub H, okay, not hat, just P sub H, minus P sub 0 equals 0, or P sub O, sorry, equals 0. Okay, there is no difference between them. They are the same. Our alternative hypothesis, okay, wanting to see if this herbicide weed killer increases cancer risk, that means the difference between P sub H and P sub O should be greater than 0. So once again, we're dealing with proportions. Okay, so this is a z-test again. But now it's not just one proportion. Now we have two proportions. A two-proportion z-test. But the mechanics work the same way, or very similarly. Okay. So here, let's go ahead and get all of our statistics down. Okay, so N sub H, so the ones who were exposed to the herbicide, there were 473, or sorry, no, there were 827 of them. 473 of them were exposed or developed cancer. Okay, so 473 divided by 827 is equal, ooh, 57.2% developed cancer. That's a lot. Our other group had 130 dogs in it. 19 of them developed cancer, which is 0.146. Okay, so obviously these proportions are very different. 57 versus 14. Okay, but are they different enough? Do we have enough evidence to say that they are different? And that's what this is all about. So it's a z-test. So we have the z statistic, okay, the z-score, which our z-score, or any test statistic, really what we observed. Okay, so the difference between our two sample proportions minus what we expected, okay, the null hypothesis, divided by the standard error, in this case of their difference. And so to calculate the standard error, well, to do this, I guess kind of in a way, we just use the Pythagorean theorem. So the standard error of their difference now, this time we can't really use the P and Q from the null hypothesis because we don't know what they are exactly, and we need concrete numbers. So we're going to use P hats for this. So we calculate it the same way that we would for just one of them. So let's see, 0.572 times 0.428, okay, P hat sub h times Q hat sub h, 1, which is 1 minus 0.572, divided by 827, and that's plus, because inside of these is the variance, so we can add the variances together, take the square root, that gives us the standard deviation of their difference. 0.146 times 0.854 divided by 130. Okay, and when we calculate all of that, we get a standard error of 0.0354. Okay, so let's put our numbers into our z-score. So let's see, P hat sub H minus PO, P hat sub O. Okay, so 0.572 minus 0.146 would equal 0.426 minus 0, because that's what we expect, divided by the standard error, which is 0.0354. I'm just going to squeeze this in a little bit more so I have a little more space that I can write the z-score on this line. Okay, so 0.426 divided by 0.0354 give us a z-score of 12.034. 12.03, fine. At that point, it doesn't matter. Z-score of 12. Okay, that is grossly larger than 2, right? So here we go. Okay. So we can reject it for 2 reasons again, right? The z-score alone, okay, so 12.03 being greater than 2 causes us to fail to reject the null hypothesis. Okay. Now, what does that look for the p-value? Okay. Now, obviously, we would expect a p-value to be very, very small, so let's find out. Go back to here. Okay, we have to use the normal distribution again. There we go. You know what? I'm going to increase the number of digits just so we can see how minuscule it is. Okay, 12.03. There we go. Calculate. Okay, I'm going to increase it to 20 digits. Maybe we'll actually have something in there now. Nope. So for a z-score of 12.03, the probability of getting a z-score of 12.03 or more, okay, the second line, it says it's 0. It's not actually 0. It's just so small that the computer treats it as 0. So in this case, we would simply say that the p-value equals 0.000, okay, which is obviously less than 0.05. And so because of that being less than our 5% cutoff, okay, from our 95% confidence, yeah, wow. Why did I say we failed to reject the null hypothesis? I was just so used to that. No, we reject the null hypothesis. We don't fail to reject it, we do reject it. So we reject the null hypothesis that there is no difference between dogs exposed to the herbicide and dogs not exposed in their cancer rates. So they are significantly different. Okay. Now we didn't actually say like how different or what the increase actually was. We just are saying that it is increased. It is larger, and that's it. We could test to see if it is a particular value, but that's outside this scope. I'll leave you to figure that out on your own. Okay. Now this is where it becomes a little interesting with the p-value. Okay? Now remember, when we reject the null hypothesis, there's the possibility that we commit a type 1 error. Type 1 error being that the null hypothesis is true, but we have incorrectly rejected it. Okay? Somehow we managed to get data that was extreme enough by random chance that would cause us to reject the null. The probability of that type 1 error is the p-value. And we see how small it is right now. So there's basically no need to worry about it in this case.